Okay, so reactions which involves carbon in that one, we will start the next reaction. Our next reaction is Baylis-Hilmann reaction. Okay, so in that one, here is I am showing that a general reaction of the Baylis-Hilmann reaction. So in that one, in this reaction, we do use starting materials like aldehyde and alpha beta unsaturated ketone, and we do the reaction in between these two in presence of basic catalysts like DAPCO. Okay, so here is the structure of DAPCO. Two nitrogen atom, it's a bicyclic compound, and in presence of DAPCO, having two nitrogen atoms, those two nitrogen atoms possess lone pair. So this is also 1 2 or 1 4 cyclo addition, sorry, conjugate addition reaction. So we will see now how to generate this allylic alcohol. Okay, so how to generate this allylic alcohol from Baylis-Hilmann reaction from these two starting materials. So I have represented which atom, carbon, or which carbon is atom comes from which starting material. So from alpha beta unsaturated ketone, we do get two carbon atoms, this carbonyl group and this carbon atom. Okay, so these two things we got it from this alpha beta unsaturated ketone, and remaining this carbon atom, and still we need one more carbon atom. So I think we would take this carbon atom from this alpha beta unsaturated ketone. Okay, so in this way we have to generate allylic alcohol. So alcohol which present at the alpha position to the carbon carbon double bond. Okay, so we have to generate this allylic alcohol by Baylis-Hilmann reaction. So now we will see what is the general requirement and what is the mechanism of the Baylis-Hilmann reaction. So the Baylis-Hilmann reaction is an organic reaction of an aldehyde and an alpha beta unsaturated ketone. Okay, so reaction between aldehyde and alpha beta unsaturated ketone. Electron withdrawing group X is equal to electron withdrawing group should be there, catalyzed by DAPCO. Okay, so DAPCO, the name DAPCO is I think common name we can say. So we so 1,4-diazam. Okay, diazam means two nitrogen atoms, diazam one at one first and fourth position, diazam bicyclo, it's a bicyclic system. You can see over here is the one six member ring, 1 2 3 4 5 6, and two 6-member ring got joined. So it's a diazah bicyclo 221 octane. Okay, so total number of atoms this 6 7 and 8. So 8 atoms are there, carbon and nitrogen containing these rings. Octane ring is there, but that one is bicyclic ring. That's why we have to call it bicyclo 222 octane. Okay, and so reaction in between alpha beta unsaturated ketone and this aldehyde in presence of DAPCO, catalyst DAPCO, or trialkyl amine or trialkyl phosphates. Okay, so three different types of reagents we can use, three different types of catalysts we can use. Nitrogen containing DAPCO, cyclic amine we can use like DAPCO, or acyclic amines like trialkyl amines also we can use to catalyze this reaction. Also we can use trialkyl phosphines. So this reaction versatile, basic reagents we can use all for trialkyl phosphines also basic, trialkyl amine basic, DAPCO is also basic in characteristics. So to achieve this allylic alcohol, so carbon carbon double bond here is Y is equal to oxygen or maybe a nitrogen or nitrogen containing. So but basically this one we have to consider Y is equal to OH. So by this reaction, we can get allylic alcohol as a major product. Okay, so this is the Baylis-Hilmann reaction. Sometimes this reaction is also known as Morita-Baylis-Hilmann reaction. Okay, so MBH reaction, Morita-Baylis-Hilmann reaction, MBH reaction. It is named for the Japanese chemist. Okay, Kenichi Morita, Japanese scientist, British chemist Anthony Bayllis, and a German chemist Hilmann. Okay, so it is named after three scientists, Japanese, British as well as German scientists. So the Baylis-Hilmann reaction in the present day version is an atom economic carbon-carbon bond formation reaction. It's a very important reaction nowadays a lot of research going on this reaction. Different variations they do in to carry out this allylic alcohol allylic alcohol compound to synthesize. Okay, so now here I have given the substrate scope. X is equal to, in alpha beta unsaturated group, X is equal to anything OR NH2 NR2. Okay, so this one is anything OR NH2. So the substrate scope I have given over here. In alpha beta unsaturated carbonyl compound, X could be the OR, means this group could be the ester group. X could be the NH2, so amide group also we can use. So different types of substrate. Y, in the case of aldehyde, Y is equal to oxygen. That means aldehydes we can use. C double bond N we can use. So different types of different substrates are there. So it's not restricted to some. Okay, only with aldehyde we can do this reaction. So different types of starting material we can use to do this reaction. Then next one, we can change these alkyl groups R1 and R2. Variety of things we can use aliphatic aldehydes or aromatic aldehydes also. Formaldehyde also we can use for this reaction. So plenty of starting materials we do have to conduct this reaction. So this reaction is specially to use to form a carbon-carbon single bond between alpha beta unsaturated carbonyl compound and an aldehyde. Okay, activated ketone or other carbon electrophiles. Okay, remember this. This is addition reaction. Whether that one may be 1,2 addition or 1,4 conjugate addition reaction. We'll see what type of nucleophile is we are going to generate as alpha beta unsaturated carbonyl compound. That means it should be the addition reaction, nucleophilic addition reaction. So first thing we have to generate the nucleophile. We'll see now in next slide. This reaction is most commonly catalyzed by DAPCO, but other tertiary amines or phosphines also can be used as a catalyst. The catalyst activates the conjugate carbonyl compound to form stabilized nucleophilic anion. Okay, so why we do pay attention at the catalyst? Because with the help of this catalyst, DAPCO or trialkyl amine or trialkyl phosphines, what is the exact use, what is the major role of this catalyst? They do stabilize the generated nucleophilic anion. So we'll see in next slide how these nucleophile they are stabilizing the your starting material, and how they are helping to attack on the electrophile. Okay, the reaction proceeds to offer the final product and regenerate the catalyst. Okay, so we'll see now how DAPCO we are going to use in our reaction, how that one is helping out to stabilize the negative charge which we are going to generate, and how we can generate at the last our catalyst. That everything we are going to explain in our next slide. So here is I have written the catalytic cycle of the mechanism. Okay, so first one we will start from over here. Okay, so this is start. Just pay attention. This is catalytic cycle I have written here. Bayllis Hilmann reaction catalytic cycle number 1, and here is the catalytic cycle number 2. Okay, so I have this catalytic cycle. I have given some other mechanisms also, but I think this is the more precise mechanism, and with this one you are getting point to point clear idea what is happening at which point, where the proton is shifting, where is the positive charge, why the positive charge is shifting, how the DAPCO is involved in the reaction, how we can regenerate the catalyst. Everything I have covered over here. Okay, so we have to start from here. So what is the explanation? The nucleophilic addition of DAPCO onto the alpha beta unsaturated ketone gives the Zwitter ionic intermediate. So first stage we have to add nucleophilic addition of DAPCO. Okay, so nitrogen possess lone pair, and this lone pair will add nucleophilically. Okay, so nucleophilic addition of this DAPCO to alpha beta unsaturated carbonyl compound to give this Zwitter ionic intermediate. Okay, so once this nucleophile is getting attack at the first position, 1, 2, 3, 4. This is 1,4 conjugate addition of this catalyst across alpha beta unsaturated carbonyl compound to generate this Zwitter ion. Zwitter ion means positive charge and negative charge, they are localized on the electronegative atoms. Okay, Zwitter ionic intermediate is nothing but the, here you can see positive charge is located on nitrogen atom and negative charge is located on the electronegative oxygen atom. So both are electronegative elements, electronegative atoms, nitrogen as well as oxygen, and these two possess two opposite charges. Where as you know, nitrogen cannot possess this positive charge for longer time. Still, that one is possessing positive charge to stabilize this our alpha beta unsaturated carbonyl compound. Okay, so the thing is, zwitterionic intermediate we have generated, which will add to the electrophilic aldehyde. Okay, so once we generated Zwitter ion, we have to add. Now this is nucleophilic addition of this generated enolate. This is enolate now. Okay, so we generated enolate by taking help of this DAPCO. Okay, so DAPCO, zwitterionic intermediate is more stabilized intermediate. Actually, you can search for this zwitterionic intermediate, what is the effect of zwitterionic intermediate. And now here we are generated enolate, and I think by DAPCO this becomes more stabilized. Now we are going to add this one. So see, first here is 1,4 conjugate addition. We have done over here. Now we will do nucleophilic addition of this enolate across carbonyl group of the aldehyde. So this is 1,2 direct addition now of this carbanion. Okay, so negative charge shifting into carbonyl group, negative then negative charge shifted on the carbon, and this nucleophile or carbanion attacks or adds to across this carbonyl group. Okay, so we are getting this type of intermediate over here.